In this video, we are going to learn more algebraic techniques so that we can use U-substitution to take integrals. So there's 4 techniques that we're going to look at, and it's going to be long division, expanding, completing the square, and separating the fraction. So we do have to do some review as we are doing this, probably because it's been a year or more since you've actually looked at these sort of techniques of long division. So for our first technique of long division, we're going to review synthetic division if we were to divide by binomial, where you have x plus or minus a number, and then we're also going to do the long division. So for your synthetic division, we already know what we're dividing by. So this value here is -2 that we're going to put in the corner of our synthetic division. Then we'll write down the coefficients of each term in order. We're going to bring down this 1, multiply with the -2, combine it with the 7, which is 5, multiply this 5 by the -2, which is -10, combine it with the 3, so this is -7. Now we can rewrite this as a polynomial. This is your coefficient 1 for x, and then your constant 5. The last number in your synthetic division is always the remainder. So this is -7 over our divisor of x plus 2. And that would be our final answer. For long division, so I'm going to write this out in long division. Do not forget your placeholder for x squared. We're dividing by 2x cubed plus 1. So our goal is to figure out how am I going to get this 2x cubed plus 1 to cancel out with the 2x to the power of 4. If we multiply this 2x cubed plus 1 by x, then I'm going to get 2x to the power of 4 plus x. And we do need to align everything else. So I'm just going to write 0x cubed for a placeholder there, 0x squared, and 0. Now we're going to subtract to find what's left over. We have -2x cubed plus 0x squared. 3x minus x is 2x, and you saw that -1. Now I'm going to do the process again. I want to get rid of this -2x cubed. I can do that if I multiply 2x cubed plus 1 by -1. So now I'm going to have -2x cubed plus 1, and I'll put my placeholders in between. Now I'll subtract everything to find what's left over, and we're going to be left with just 2x. So that is our remainder. So our final answer from up here is x minus 1 plus 2x over our divisor. That is our final answer. So now using this with integrals. When we see a fraction, and the first thing you probably want to do is use regular U-sub, but if I take the derivative of x squared plus 1, I get 2x, and that's not what we have. So we can't just use regular U-sub, at least not just yet. Whenever you have a proper fraction, then you could probably see if you could use U-sub. But if you have an improper fraction where you have a higher power in the numerator than the denominator, or it has the same power top and bottom, you're going to divide. So we're not going to use synthetic division because we have an x squared plus 1. I'm going to use long division to see if I could rewrite this integral, and it would be easier for me to integrate. Okay, so I'm going to go ahead and do that. I'm again going to put placeholders in. Okay, so if I multiply this by 1, I'm going to get back x squared plus 0x plus 1. But then we're going to subtract this. And I'm just going to be left with -1 minus 1, which is -2. So that means I can rewrite this as 1 minus 2 over x squared plus 1. I'm going to call this integral I. So I can actually be re-represented as 1 minus 2 over x squared plus 1 dx. And this is what we're going to integrate. The antiderivative of 1 is just x. This 2 is just a number, but I know what the antiderivative of 1 over x squared plus 1 is, and that's tan inverse. And then we're done. That's our final answer. Here's another method. This is the expansion method. So whenever you have something that you can always expand on, like a product of factors, you can expand it and see if that's easier for you to integrate. So I'm going to go ahead and expand sine x plus cos x all squared. Then I'm going to get sine squared x plus 2 sine x cos x plus cos squared x dx. Okay, and then now I'm going to change this because I know that sine squared x plus cos squared x is 1 according to the trig identity. So this is now just 1 plus 2 sine x cos x dx. And I can separate this even more if I wanted to. Because I know how to take the integral of 1, it's just going to be x, but this one here does require me to use U-substitution. So we can let u be sine x, because we're just going to get back cos x after we take the derivative of sine x. So du is cos x dx then. I'm going to continue this up here. We can integrate the 1, which will be x. And then I'm going to replace sine x with u and cos x dx with du. And then integrate that. So the integral of u is going to be u squared multiplied by a half. And we have an indefinite integral, so don't forget your plus a constant. The ones are going to cancel out. And then we're going to replace this u back, which was sine. And then that is our final answer. Technique number 3 is to complete the square, but we're going to review how to do that first. So to complete the square, your next term here is going to be the b value divided by 2 and then squared. In other words, it's 8 over 2 squared, which is 16. And this would be x plus 4 all squared if we wanted to factor that and complete the square. For the next one, this will be 11 over 2 squared, which is 121 over 4. And if we want to factor this back, this is going to be x plus 11 over 2, all squared. Now we're going to go ahead and do this with an example with an integral. So every time you see a number over some sort of quadratic, you can maybe try to complete the square and see if that would help. So you could integrate it in an easier way. So we're going to try to complete the square in the denominator. So 6 divided by 2 is 3, and then squared is 9. Then we're going to subtract that 9 and the 10. this is what we're going to try to factor. So this will be x minus 3 squared, and we're going to combine the negative 9 and the positive 10, which is just 1. Now we're going to use U-substitution because I can let u be x minus 3, and we know that 1 over u squared plus 1 is tan inverse of u. So u is x minus 3, then du is going just to be dx, then I'll do the replacing here. So 2 over u squared plus 1 du. This 2 can just technically go in the front of your integral if you wanted to. But once we take the antiderivative, this is 2 tan inverse u plus a constant, which is 2 tan inverse of x minus 3 plus a constant. And that's your final answer. The last technique we're going to cover is to separate the numerator. So when you have more than one term in the numerator, you can separate the numerator and then leave your denominators alone. So this will be x squared over 6x plus 2 plus 8x over 6x plus 2. For the next one, it'll be 5x over 1 plus x squared minus 4 over 1 plus x squared. So this term, if you were to integrate that, that's going to be tan inverse. If you want to integrate this, you can use u sub because 1 plus x squared, that derivative is 2x, and we could just manipulate those coefficients at the front. Okay, so now we're going to do an actual example that utilizes this method. So I'm going to separate this into 3x over the root of 1 minus x squared dx plus the integral of 2 over the root of 1 minus x squared dx. So I'm just separating it like that already because I know I need two different methods in order to take the antiderivative of them. Now, before I continue on, just as a side note, we couldn't let this be u because then the derivative of this is negative 2x, but it would be fine if I just had a 3x here, but I had this extra plus 2. So I can't just let u be 1 minus x squared because I don't actually have the right derivative in the numerator. But if I separated them, that's fine. Now I can use u as 1 minus x squared, and I don't have that plus 2 to worry about. And I'll use U-substitution for the first one. This one is just going to be sine inverse after I take the integral of that. Okay, so I'm going to let u be 1 minus x squared. Then du is minus 2x dx. We don't have this minus 2, so I'm just going to move it to the other side. And then do my replacing. Okay, so this 3 I'm just going to move to the front. I replace the 1 minus x squared with u. And then the x dx was replaced by negative 1/2 du. This one is just 2 sine inverse x after I take the integral of that one. And remember to add a constant because we have an indefinite integral. Now I'm just going to move this negative 1/2 to the front with the 3 and change our 1 over root u into exponential form. Now I'll integrate that. So this will become u to the 1/2 multiplied by 2 and then I'll replace the u with 1 minus x squared. I guess that 2's gone, so I'll erase that. and we are done here. You could also change the exponential form into radical form if you want for 1 minus x squared. So let's recap all of our techniques. The first one's long division. You're going to use long division when you see that the degree in the numerator is greater or the same as the degree in the denominator. You want to complete the square when you see a quadratic in the denominator and a constant in the numerator. You want to separate the numerator when you have more than one term in the numerator. And you will expand when you see the derivative of the inside function is not on the outside. So in the next page, I have 4 questions that you can try on your own. And then when you're ready, press play to see the solution. Okay, here are your solutions for example 5. For A, you're going to use long division so that you can get x cubed minus 6x plus x over x squared plus 6. So you know to do that because if you take a look at the powers, we have a higher power in the numerator than in the denominator. Then once you divided and replaced your original integral with the divided integral, you're going to use your power rule and reverse it for the first 2 terms, and then for the last term you're going to use U-sub. For example 5b, you want to complete the square here. We have 1 in the numerator, and then in your denominator we have a quadratic. So once you complete that square, that's going to be x minus 2 all squared, and then you're going to replace this x minus 2 with u and do your u substitution. For c, you're going to separate the fraction. So you're going to e to the x over e to the x for the first term, which is 1, and then 4 over e to the x, and then integrate it from there. You could also use u-sub if you wanted to, and say u is equal to negative x, and then du is equal to dx, or negative dx if that's what you wanted to do. But you don't have to. You could have done that integration without using u-sub. For example 5, d, you're going to expand that. So it's x to the power 3 minus 7 times x to the power 3 minus 7. Then you're going to integrate each term after that. So there's 2 more questions I want to go through with you. Sometimes you can use u-sub, but it doesn't account for all the x's in the integrand. So you could make another substitution after normal substitution and then replace everything in terms of u that way. You're going to see what I mean once we do these 2 examples. So for this one, I'm going to let u be 2 minus x because the derivative of that is just going to be a negative 1. And then you're thinking, why would you do that? Because we don't have this x. when I take the integral? Well, we can replace that x. What if I just said that x is equal to 2 minus u? And that is certainly true. I just moved the x to the other side and the u to the other side. And now I can write x in terms of u. So if I just do my regular u sub, I would get this, but then I still have the x there and I don't want that. So I'm going to replace this with 2 minus u for my x. And then simplify this, then take the integral. So this is going to be 1 minus u root u du, and I took the negative out. And then I'm going to expand. So this is root u minus u to the power of 3 over 2 du. Now we can integrate. So this will become, well, this is u to the half, so I had to add 1 to that. That's 3 over 2 multiplied by 2 over 3 minus u to the 5 over 2 times 2 over 5 plus some constant. Okay, and then I'm going to distribute my negative and also replace u. And that will be our final answer. For our next one, I'm going to do the same sort of thing, because if we let u be x plus 4, we won't exactly get back to x plus 1, but we can rewrite this x in terms of u. And I can rewrite this as x is equal to u minus 4. Okay, so this integral then, if I do some replacing, it's going to be root u. The dx is just going to change to du. And then for your 2x plus 1, I'm going to put in u minus 4. So 2 times u minus 4 plus 1. And then simplify this. So that is 2u minus 8 plus 1 all over root u du. Then we have 2u minus 7 all over root u. Then I'll separate each term. So 2u divided by u to the power of half, same base, subtract exponents. So we have 2u to the power of a half minus 7u to the power of negative a half. Then we'll integrate this. So I'll just leave the 2 in the front here and integrate this u to the power of a half. So this is going to be u to the 3 over 2 times 2 over 3 minus, leave the 7 in the front, add 1 to negative a half, which is a half, multiply it by 2, then plus a constant. So we have 4 over 3 u to the power of 3 over 2 minus 14 u to the power of a half plus a constant, and I'll put the u back in.